in the last class we were discussing that Hessian not only give you access to that is a real minima or not, it can also give you access to spectroscopic properties, and the spectroscopic properties which is related to Hessian is vibrational spectroscopy. We are going to discuss both IR and Raman. Remember, spectroscopy and quantum mechanics has a very intricate relationship. Quantum mechanics started with some kind of a spectroscopy. Don't forget Max Planck's black body radiation. That's where the actual quantum mechanics began. And to interpret spectroscopy, quantum mechanical calculations are widely used. So, we will start with the IR spectroscopy. We know that infrared spectroscopy is study of absorption and emission of infrared radiation, which might result into vibrational transitions. IR radiation mainly lies between visible and microwave in this case. They can be broadly classified into three regions actually. The near IR is from 14,000 to 4,000 centimeter inverse, middle IR is 4,000 to 400, and far IR is from 400 to almost 10 centimeter inverse. So, the principle of vibrational spectroscopy is that the energy applied in the form of infrared radiation that causes vibration between the atoms within the molecule, and when the frequency of the absorbed IR radiation is equal to the natural frequency of vibration, absorption of IR radiation take place, hence a peak is observed. Every bond and moiety within the molecule have different natural frequency of absorption, and different chemical bonds may have more than one mode of vibration. Each vibrational mode has different frequency for absorption with the peak in the different region of IR spectrum, and a collection of such will give a distinctive spectra for different molecules that help in the elucidation of molecular structure and identification of different kind of bonds between the different atoms. So, this is a quite useful tool if you want to find what kind of functional groups are present in your molecule. So, about the different vibrational mode, this is of course a topic of some undergraduate chemistry course. I will just quickly recap. So, there are there are only two kinds of vibration. One is stretching and the other is bending. The stretching can be also symmetric and asymmetric stretching, and for the bending it can be in plane bending, scissoring and rocking, and out of plane bending, wagging and twisting. One can calculate all this vibrational mode using quantum chemistry calculation, and we will see how. So, to do this quantum chemical calculation, let us say we are doing a quantum chemistry calculation for a diatomic molecule which contains a bond. The potential energy surface will look like this. So, what we will do? We will take an harmonic oscillator approximation, and of course, this is my electronic potential energy surface. Remember, it is called potential energy surface because nucleus move inside this potential, and these are my vibrational level. So, in most of the case, the spectra we are interested comes due to the vibration from the ground state to the first vibrational excited state, and that can be modeled very well using an harmonic oscillator approximation. Now, in the harmonic oscillator approximation, of course, the level separations will be identical. Here, the actual separations are not identical. Once you go, the vibration levels becomes closer and closer, and for that you need to consider the anharmonic effect. But for the transition from the 0th to the first excited state of vibration, generic harmonic oscillator approximation is a very good approximation. So, the absorption and emission of IR radiation can be understood using a quantum mechanical simple harmonic oscillator, and the frequency oscillation for this model is given by Hooke's law. The energy levels of oscillators are quantized, and the transition of absorptions are governed by the selection rule. Delta nu is plus minus 1, that is for a purely harmonic oscillator, and for a molecule to absorb IR radiation and to show transition, it should induce a change in the dipole moment of molecule. So, it is not that every molecule will be IR active or every vibrational mode in a molecule will be IR active. Now, this is the potential energy surface of a polyatomic molecule expanded in the Taylor series. So, you see that this is the first term, and then the first derivative of the potential, second derivative of the potential, and if you go to the infinite order, this will give you the exact potential energy. Now, one can, so in the previous slide what we have seen is a one dimensional vibrational Schrodinger equation for the harmonic oscillator problem. Similarly, one can extend this one for a polyatomic molecule by writing a multidimensional vibrational Schrodinger equation. So, problem with that, this is not very easy to solve. What one can do is that one can switch from the Cartesian to a mass dependent spatial coordinate q, and then it will be possible. So, this has a dimension of this multidimensional vibrational Schrodinger equation actually has a dimension of 3n. Now, what one can do using mass dependent spatial coordinate Q is to separate this 3n dimensional equation into 3n one dimensional Schrodinger equation, like a harmonic oscillator kind of an equation, and then one can solve it one by one. So, each component of Q correspond to a molecular vibration, that is generally called a normal mode. I will not go into discuss why it is called a normal mode. You should consider some spectroscopy course for that. One thing to remember here is that how I got this mass dependent spatial coordinate is basically diagonalizing a mass weighted Hessian matrix. So, the second derivative matrix, if I diagonalize, I will get what is called this mass dependent spatial coordinate. And things to remember, the vibration analysis is only valid at the equilibrium geometry, calculated with the same method and basis set. So, to do any vibration analysis, to draw any spectrum, I have to calculate the frequency at the same geometry at which I have optimized the molecule. So, my method of geometry optimization, method means both the theoretical method and basis set, will be same, has to be same as for the optimization as well as the frequency. Why so? See the form of the potential energy surface. So, it actually has a gradient term. Now, only at the minima this gradient term will become 0. So, then I can my first dominant contribution will come from the Hessian, and that is where I can do this analysis properly. If I use some other geometry other than the minima, the vibration analysis what we do has very little meaning. Of course, one can see the mode of vibration and then can decide it is a real minima or a potential surface. Sometimes looking at those modes helps you to find out, to tell you under which direction the transition states will be, along which direction you can find the minima. Other important thing I forgot to write it here is that often it is called a negative frequency. Remember, what you calculate frequency actually correspond to a square root. So, the proper word is an imaginary frequency, negative frequency is a loosely used word. So, now let us do some calculation. So, these are IR spectra of formaldehyde. So, you see there are various modes. So, the stretching modes are at the top, bending modes are at a higher wavelength, higher frequency, and the remember frequency and wavelength is inversely related. So, the correct statement is the vibrational the stretching mode is at higher frequency and the bending mode is at lower frequency. Let us do the calculation. So, let us go to Avogadro, let us draw formaldehyde. So, this is carbon. I should not have adjusted the hydrogen. So, let me draw carbon, and next I add the oxygen, make the bond double. Now, I need hydrogen, of course, with single bond now, and I can give it a quick optimization to make it a formaldehyde. I go to extension, generate Orca input file, I will put B3 lip, opt, fric, I want to use Rij cos x, and maybe def to TZVP. Let us see what is the basis set I wanted, VPP. So, generate the input file, let us name it H2CO. Go to the directory IR, I could have used move exterm. Let me zoom it in a little bit. maybe a further. That's actually started solving the Hessian. So it's done. So what we can do now, we can go to the IR geometry and open the output file using ChemCraft. Of course, the optimization step is there. I am not going to look at it. I am directly going to look at the frequency. So it has 4 atoms. So number of vibration mode will be 4n minus 3, 4n minus 6, sorry, because 3 of transition, 3 are rotation. So these first 6 frequencies are 0. Maybe first we will look at the output file first. So if I run a frequency calculation, this is where I will get the IR spectrum. This is what the frequencies are. These are first 6 frequencies are 0, and these are my vibrational modes. So here what you cannot see is the vibrational modes which are actually with respect to the symmetry. So to do the calculation with respect to the symmetry, what we should do is to go to the input file. Orca can actually take care of the symmetry. I think we have not discussed it so much here, and the keyword to use it is use sim. So now it will run it with the symmetry, and let me quickly run it here. And by the time the symmetries are done, we can identify them. Let me close it for the time being. So now you see, when you use the symmetry, it's detected to a C2V. So the point group is C2V, and let's C2V, we know there are 4 rewraps, A1, A2, B1, B2, and the molecular orbital, there are 5 corresponding to the occupied orbital, 5 corresponding to A1, 2 corresponding to B1, 1 corresponding to B2. It went into the Popper linear solver. Yeah, so now if you want to see the IR frequencies, this is how it will look like. Remember, to calculate the frequency also requires the intensity. So the intensity is actually related to the mixed derivative of the energy with respect to both geometry as well as electric field. So these are basically the geometric derivative of the dipole moment, and this is where the irreducible representations are given for each of the vibrational mode. Let us now open it with the ChemCraft, and we can try to visualize the vibrations. So let us start with the lowest energy one. So this is a wagging. This is a bending mode. The previous one was a wagging. This is a rocking mode. The 15 one is a seizure. 1818 is a stretching of the CO bond. 80.16 is a symmetric stretching, and the highest one is an asymmetric stretching of the CH bond. So, this is all the vibrations where, and if I want to see the spectrum, you have to click on optimization and frequency, show spectra, IR intensity. This is how the spectra looks like. Of course, this is not what an IR spectra will look like. So, I will use some kind of a broadening, Gaussian or Lorentzian, and if you want to go to the style of the plot, so what you can do is that here multiple options are given how to do this one. I believe there should be an option to reverse the axis. Yes, it is here. So, I will invert the x axis, so it will come like this. I can copy this picture and put it close to the experimental one. Maybe I have to reduce the size a little bit. So, if I keep it here, you will see that the picture looks almost same, maybe the spacing is slightly different. Of course, these two are not according to the scale, but if you see the shape of the spectrum, you can identify all the modes. This is the asymmetric stretching, this is the symmetric stretching, this is CO stretch, this one is actually the CH2 Caesar, this is CH2 rock, and this is CH2 wagging. So, these three are the spectrum. So, you can reproduce any of the spectrum you can do here. One of the important thing is that in many of the, and you can compare it here. Maybe I should open an Excel sheet and write my calculated values in front of the experimental value. I believe I already have a sheet with that, with the experimental one. This is calculated freak. Actually, these are web numbers, to be really honest. And you can find out the values. Oh, I went to the wrong sheet. This one should have been the one. Yes, it's already written the B3 lip in. So, these should be the values, and I should also copy the intensities. Of course, the experimental intensities are in arbitrary unit. Now, one of the important facts, so if you see that the values are slightly overestimating than what you get from the experiment. Now, errors in the IR spectra are often quite systematic. The Hartree-Fock method, especially if you do a Hartree-Fock calculation, it's overemphasize the bonding. So, all four constants are too large, and thus called the frequencies, because the bonding is strong means it requires more energy to stretch those bonds. Now, application of a constant scaling factor to Hartree-Fock frequencies or to any other calculated method can improve their accuracy enormously. So, it's fine to scale your calculated values by a constant number. So, the ORCA keyword for that is scale freq. So, in the frequency block you have to use the word scale freq, and for the method we have used B3 lip TZ VPP, you can use a scaling factor of 0.985. So, here it contains the detailed table for various kind of method, what should be the factor one should use, and what kind of things what will give you what will be the corresponding errors. But and this is only a limited list. For a more updated list, you should go to this site from where I have taken this value of 0.985, but if you already have, so either you can in the beginning of the calculation you can give this scaling frequency in your input file and will scale it accordingly, or if you are using ChemCraft, what you can do here is that there is an option to scale the x and y axis. So, the x axis you can scale and so this will now got scaled. So, you can copy the same values and you see now the numbers are much better agreement with the experiment than what you are seeing it from the beforehand. I believe these two values are wrong, because this is CO stretching yeah, it is 2782. By mistake I have written 1782. So, now you see for all the modes actually now the agreement is much better than what is obtained from the unscaled variant. So, it is always a good idea with the scale to use the scaling, and its spectroscopy it's a common practice to scale your calculated result by some parameter to get a better agreement with the experimental result. Now, for a homework problem, we have calculated the CO stage value of formaldehyde and we have seen what are the calculated values. So, the unscaled value is 1818, the scaled value is 1790. So, now you can calculate the CO stretch IR frequency for acetone and acetyl chloride and compare with formaldehyde using the same level method. Even you can compare both the scaled and the unscaled version, how the difference comes, how much is the shift due to the change in the environment.